chart shows something different actually.
Okay. Did anybody get it to work? You got it to work? Can we see your code? Yeah, but also it's not clear on the. Is there a way to make it clearer? Yeah, I can't. The script doesn't zoom. That's the. It's better if I make it shorter. Which one? Hold on, I'm trying to make this. Click on the screen. Here. Yeah, I don't have the hand.
In edit GUI preferences size. Edit in R itself main toolbar edit GUI preferences size.
Yeah, other option, right? But if I go to display settings, and yeah, there, slightly better. Okay, so first thing was we loaded the library or dsol. Everybody should have at least gotten that far, right? And the second step is to write your working directory. This is where I have it stored, but you would have one. So our qin was a function of time. If it was less than 10 days, it started off at 10 and went up to 100, and then it went to 125 after 10 days. So I just used an if-else statement, and I put if t is less than 10, that's the equation 100 plus 2.5t, else q is 125, and the function returns the q. Okay. Our inlet concentration is also a function of time. So if t is less than 10, c is 10 plus 0.9t, so it goes from like 10 all the way to 100. If it's greater than 10 and less than 100, then it's just 100, okay? And if it's greater than 100 and less than 110, it drops back to 10, and then if it's greater than 110, it's 10. Okay, so I return. So I use like 4 if statements rather than do an if else, if else, if else. You could also do a case statement if you want, like switch and write it that way. It's up to you. Okay. So the third part is to write the derivatives. So I bring in 3 parameters. E is the evaporation rate, Q is my outflow rate, and then K is the first order decay coefficient for my pollutant. They are all coming out of params, so they have to be in this order 1, 2, 3, E, Q, and K. Okay. Then my dVdt, this is my flow, is Q in as a function of t. My q in, remember, is a function that I wrote. And then minus q, which is the outflow rate, minus the evaporation. Okay. The second one, dc dt, is I have to pull out whatchamacallit, so q in t times c in t, that is the one that we expanded using chain rule. When I have the dVdt term, I can plug in the first mass balance equation and do all that stuff. The only thing is x, since my x is what I'm using here for my dependent variables, the state variables, I have x1 is my volume, x2 is my concentration. So anytime I have to use concentration, I use x2. Anytime I use volume, I have to call it by x1. So then I combine these two, and then I list it out. Like, so this is the function that goes into dsolve, like that we have to provide. But this function itself is calling 2 functions, qin and also cin are the functions. So remember that if you want to send this into dsolve, the first should be the time, second should be your variables, okay, the state variables, and the third should be the parameters that should go into this. So it should be in that order. Okay. So here I write my inputs, E, Q. I have a half-life that so this is my half-life. And so I'm writing my input E is equal to 1. This was my 1 meter cube per day ET or evaporation. Q out was 75. Half-life was 20 days. I convert that to K using log 2 over T half. And then my parameters have to be in this order E, Q, and K because that's what I said in the code. My initial condition is 1 meter cubed and then 0 milligrams per liter. So those are my initial conditions. And then my sequence, I'm going from 0 to 365 in whatever time step you want. I was going there with 1 day. If you want half a day, that would be, you could turn that out. And then my solution using LSOTA is the first has to be the initial conditions, the second has to be the time, third has to be the function, and then you send the parameters. Okay. So if I run that, I wouldn't advise you to run all at once. I knew this, I ran it half and half before, so I know it works, but generally speaking, don't write everything and then try to run it. It's pretty bad. So if I go plot T, and this would be my flow, and my flow just keeps on increasing, which is what, because in the reactor, the volume of the reactor keeps on increasing. Okay. And then if I plot remember the first column has the time, so and you'll see a curve that looks like this. There was nothing in the reactor. As the contaminant started coming, the concentration went up, but then we started putting a lot of flow in it, so dilution kicked in along with the degradation, so it kind of went down, and then you'll see a small variation right around that 100 to 110 day because my concentration dropped there, like my inflow concentrations dropped there, and then kind of virtually went out. Okay. So if you have time varying volume, like so if you do a sequencing batch reactor, if you design a sequencing batch reactor, you would write a model very similar to it, except you would have a filling stage where you would have both of these models, and then there is a reaction stage where you're not putting any inflow into the model, so that would be a batch reactor, and then there is a stage where the water is drained. Again, the model would look very similar like this, but it would start with a different initial condition. It would start with full and then go down. So we wrote the model for batch reactor, we wrote the model for CFSTR. The sequencing batch reactor simply puts these at different stages, and then it will simulate the different processes associated with treating contaminants. This could be ex situ treatment of contaminants that we pump out. A lot of times when we have geogenic pollution, we have a lot of contamination, so it's very hard to do in situ treatment because it's not localized, it's not at one location. So invariably, we tend to do ex situ treatment with geogenic pollutants. We don't treat it unless we have to. Okay, so sequencing batch reactors are very common with treating geogenic pollutants from groundwater, fluoride, arsenic. We tend to sorb out or use adsorption as a mechanism. So either we have to construct a column or we have to construct a batch. Usually if you have if you're using some sorbent that is very fine grained, you have two choices. One is to make a sequencing batch reactor or a batch reactor where you're reacting, or you coat it onto a more porous material and then make a column or a filter and pass through it. Filters, the disadvantage is you lose a lot of mass where in the reactor where there is no reaction taking place because you're coating only on the reaction only happens on the coating. The advantage is you can connect that filter onto your tap and it's very convenient. On the other hand, if you have a sequencing batch reactor, somebody has to fill it, drop it. There's a little bit of control that needs to be done. So, but on the other hand, you exploit the full surface area of your adsorbent because your entire adsorbent gets to react in this case. it's not so in a filter or in a plug flow type system. So we'll get back to R, do some more coding, but what I want to talk today is, if it cooperates, talk a little bit about hydrologic site investigations. And so when you have contaminated sites or remediation sites or sites where you want to perform remediation, whether you have contaminants, the first thing you want to do is go do some hydrogeological site investigations. Okay, so what we do in a site investigation, the idea behind the site investigation or the goal of the site investigation is to create what's called as a conceptual site model, like or CSM. And what CSM does is it helps us tell what contaminants are present, what are the sources of these contaminants, where are these sources located, when did the contamination happen, what was the likely source of that contamination, what's causing that contamination. So the idea is to track your contaminant from the source all the way to the receptor points. Okay, so a receptor in risk assessment is an organ on your body or something in your body that gets attacked by that contaminant. So a receptor point is where you start getting exposed to that contaminant. So a well would be a receptor point in groundwater, and similarly you could have non-point receptor points like air. If you're air pollution, it's there everywhere, so an intake of a water treatment plant in a surface water stream is a receptor point. We tend to put the word point to differentiate it from receptor, which is actually the organ in your body that gets attacked in risk assessment, or that gets attacked by that contaminant, causes effects to the contaminant. So the idea of conceptual site model is to somehow track your contaminant from its source to potential receptor points in that area. So what that tells us is how are people getting exposed. So a fundamental tenet of risk assessment is to say what's your exposure and what is the risk associated with that exposure. So before we do risk assessment, we do what's called as an exposure assessment, and that exposure assessment basically tracks the contaminant from the source to whatever location, into that receptor point, and you say, okay, who's getting exposed and through what pathways. Okay, so what are some of the pathways in which you can get exposed to groundwater contamination? Okay, so the consumption, if you drink water, then ingestion of that you could ingest contaminants because you're drinking water. Okay, what else can happen? Infiltration into. So what are the 3 or 4 mechanisms of exposure? Ingestion, inhalation. So is inhalation a problem in groundwater pollutants? Dermal contact. Okay, we'll get to dermal contact, but is inhalation a problem? Inhalation could be a problem, especially if you have organic contaminants. Okay, so if you have trichloroethylene or benzene or other types of organic contaminants, they tend to be volatile. So when you bring it indoor, the water, it'll start giving out fumes, and especially you get very close exposure because you're drinking from a glass, and if the water is contaminated, your nose is pretty much in the glass, so you inhale it, you have no other choice. So while ingestion, there could also be inhalation efforts. Another place where inhalation plays a very big role is when you take a shower. So because you're heating that water, and usually that means that any dissolved organics will tend to volatilize, like, so the volatilization process becomes higher. So your water is at what, 40 degrees Celsius, 50 degrees Celsius, as opposed to being at like 15 or 20 degrees Celsius when you're drinking it normally. So your inhalation hazards actually go up when you take a shower. Of course, during shower, you also get dermal contact. So that same chemical is now touching your skin. The water is touching your skin, so you will get contamination, because of that. And our body is organic, so it like attracts like. So a lot of organic contaminants will tend to prefer your skin over being in that water. So they will partition and get into your skin. So that's the dermal contact. So there is one more path, which is injection. Very rare, but sometimes if something gets injected that's contaminated, a lot of pharmaceuticals or medical, they do use a lot of water, when they make their solutions. And if that's contaminated, then, and you inject, a vitamin or B complex or whatever injection you take, you may end up getting contamination. So, but that's a very, very small pathway. Usually that pathway is not big for us, but ingestion, inhalation, and dermal contact are the three processes. And you can actually have all these happen with groundwater. So it doesn't mean that the inhalation is always related to something being released in the air. It doesn't mean that dermal contact will only happen, because of air being, in contact with us. It can happen with any media, it depends on the type of pollutant. In addition to humans, we also look at what are called ecological receptors. Ecological receptors are like fish, like plants, because we also get indirect exposure, because we're not using the water, but the water is being used to grow something, and contaminants may actually move from the water phase into that food or fiber or whatever it is, and then you ingest it, and that's a form of, it's a secondary ingestion or a secondary source of contamination. In most, since we're in Bengal, fish is a big thing here. So a lot of contaminants end up going and depositing in the fatty tissue of the fish. Okay, so that's called biomagnification or bioconcentration factor. So the concentration in water could be like 1 milligram per liter. By the time it gets into the fatty acid of the fish, it becomes probably 10 milligrams per liter, because that 1 milligram is spread out over a very, very small portion. Like instead of 1 liter of water, it's now in that very small portion of that tissue mass. So that causes the denominator goes down, which means your concentration has gone up. So that's called biomagnification or bioconcentration factor. So now you eat that, enjoy that slice of fish, and that's back in your body. So that's how contamination moves. But fish are not the only culprit. Vegetarians are not susceptible to getting risks. A lot of fruits and vegetables that we eat are all organic. So if you have organic contaminants, they tend to preferably go into organic contaminants. So if you take wastewater, or if you take contaminated water and irrigate your crops, there's a good chance that contamination will partition from your water into that crop, and then eventually you will consume it and take it. So, and the downside of this is once an organic chemical goes into an organic substance, it's very hard to remove it. Whereas if it goes into an inorganic substance, or if it stays in water, which is an inorganic substance, it usually has lesser affinity, so it tries to get out. Especially if it's volatile, it'll try to go into the air phase. If it is or it'll try to go into organic phase. So if it finds an organic phase, chances are an organic matter will go to organic phase. So bioconcentration or biomagnification in fish and food products are a big issue, especially if you use contaminated water. So those are secondary pathways. Those are important to us too. The primary pathways obviously are you coming into direct contact with that groundwater, and sometimes you may not have to come, as you might be drinking water, but you may be inhaling contaminants that are coming out of it. Like, another big problem that has happened, that has gotten a lot of attention in some other countries, but not in India, is vapors from groundwater, contaminated groundwater, getting into buildings. Okay, especially if you have very low-lying buildings or under shallow water table, that contaminant can actually diffuse, go through some of the cracks in your foundation, and get into your buildings. Okay, in many countries, in many countries where we don't have AC, we keep our windows open. Okay. Good thing, bad thing? Good thing also, bad thing also. Like, especially if you're getting contamination from groundwater, it's a very good thing because it will just get diluted. But if your air is as polluted as the groundwater, then you have a bad thing, like your contaminants coming. But in many countries, especially the U.S., we have closed buildings, which means we can't open our windows. They are sealed. The window looks like a window, but you can never open it because they want to keep the air condition just flowing, and they don't want the air cool air to like leak out, because that will take more energy to like cool that air again. So once the groundwater contaminated, once some vapors from the contaminated groundwater come into that building, it stays in that building for a while before the air condition sweeps out that air and replaces it with fresh air. So your exposure is much higher. But on the other hand, if you have places where you can open windows, that contamination risk is a little low because you are mixing or diluting water and diluting air with that contaminated air. So only downside is if your air is more contaminated, then you have another problem. But that aside, so that could be another pathway of interest too. So it is soil to soil vapor pathway, or what we call as the soil vapor migration pathway. So it's the soil vapors that are migrating and getting into buildings. So part of this site assessment is to look at all of these things: who are the receptors, what not, and the second part is to collect geological information. Okay. So how do we collect geological information? So one is so before we do that, the hydrogeological site investigations, we break that into three parts. One is what's called as the contaminant characterization. Second is called the geologic characterization, and the third is the hydrologic characterization. Okay. Contaminant characterization, as I said, you need to look at what contaminants are present in the field and what are the likely exposure pathways. Is the contaminant volatile? Can it get into air phase? Is the contaminant has an affinity? Is it hydrophobic, which means it can be in water, but if it comes into contact with something else, it will tend to move into that phase rather than stay in water. So hydrophobic contaminants tend to escape out whenever they get a chance, and they prefer any organic matter. So if they come into contact with any other organic matter, like your skin, it'll go there. So the type of a contaminant, what it is. If you're looking at metals, and if you're looking at inorganics, the pH plays a very big role. The redox chemistry plays a very big role, because groundwater is under reduced environments. If you bring it to the atmosphere, if you bring it to the surface, you are oxidizing it, and that will change the valence of your chemical. So your chemical mass has not changed; it's just gone from being in one state to another. Very common is iron. You will see rust stains right outside of wells. It's very common to see rust stains on wells. That's even if you put a PVC well, you'll start seeing rust stains on it after a while. The reason for that is you have ferrous in water, so there's a lot of iron in water, especially in Bengal. There's quite a bit of iron in this water, and if it's in the groundwater, it tends to be in the reduced form. If it comes out and gets exposed to the atmosphere, it goes to the oxidized form, so which means it goes from being Fe2 plus, which is ferrous, to Fe3 plus, which is ferric, okay, because the other form of oxidation is removal of electrons is oxidation. So the more plus, the more reduced; the less plus, the less reduced. So That's what happens, and then ferrous, of course, precipitates out, or ferric precipitates out, forms that coating. Okay. I still live in Maine, which is on the northeast side of U.S., and there's a lot of iron and manganese in that aquifer too. And then it used to get really cold. It's one of the very cold places because it's high up in the latitudes. So we would have this lakes that would freeze, or at least the surface of the lake would freeze. The bottom of the lake is always there's water because of the way water works. Like the ice kind of traps the heat and keeps the water, right? But that water there is no oxygen going into because of the stream, because of the ice coating. There is no oxygen going into that stream, so the water is under very reduced condition. Groundwater tends to be a little warmer, so there is still groundwater discharging into these lakes during winter time, but it's all under reduced condition. What happens when spring comes, when the summer temperature comes, that ice melts and oxygen starts to flow into the lake. The lake turns red, because all the iron that was coming into that subsurface water just precipitates out. Okay, so you could go in spring and look at the lakes. It almost felt like somebody killed a bunch of people and then throw their bodies in there, so it would be that red. I mean, of course, Maine was a very less populous state, so if that really happened, people would know really quick who died and what would have happened. But it was all the iron that would come out, because of precipitation. So chrome 6, chrome 3, I talked a little bit about that. Chrome 6 is extremely mobile. Chrome 3, on the other hand, is very immobile. So chrome 3 is in the reduced form, chrome 6 is in the oxidized form. So if you change it from chrome 3 to chrome 6, it could be chrome 3 in groundwater, but when that groundwater discharges into surface water as base flow, it will get open to oxygen and then it becomes chrome 6. Chrome 6 is extremely toxic. As a matter of fact, the way we treat chrome 6 is to turn it back into chrome 3, and by changing the redox condition and then passivate it, so it becomes mobile and then starts to move. And it can move for miles and create some very large scale contamination. I talked about a civil action movie. If you get a chance, there's a movie called Erin Brockovich. If you find it, you can see it, starring Julia Roberts as Erin Brockovich. It talks about chrome 6 contamination in Southern California, because there was a lot of chrome 6 used in electricity production, and that had caused widespread contamination in Southern California aquifers. And this one lady goes about digging how to what went wrong, and so talks a lot about chrome 6 contamination. Pretty interesting movie. So that's what we do with contaminant characterization. A lot of times we just take a sample, send it out to the lab, and get a slew of measurements made because we don't know what's in there. So typically, if you're looking at organics, we look at hydrocarbons, we look at gasoline range hydrocarbons, we look at diesel range hydrocarbons. If we know that it's Air Force or if it's a site, site where there were planes. We look for jet fuel, we look for kerosene, things like that, which are a little bit more high molecular weight. Diesel is another big contaminant, slightly higher molecular weights. Gasoline is the very low end carbon chains, typically C4 to C12. Diesel is more in the C8 to C14, C15 range. Jet fuel and kerosene are more in the C15 to C20 range, 20-25 range, and then you have coal tars and stuff which are C30, C25 range. So they tend to be almost like a semi-solid or a solid. But as you move from C4 to C30, C4s tend to be very volatile. They tend to be in the air. So if you get them in water, they escape. If you've ever gone to a petrol bunk and you can smell petrol, you're smelling butane and other isopropane, so C4, C5, C3, C4, C5 compounds. The middle range, which are the aromatics, especially benzene, C6, C7, that range, they tend to be relatively soluble in water. And then as you move into more C8, C10s, they tend to have a lot more affinity to organic compounds. So they will stick to the soil organic matter and just stay there. So you will see that changes. There are pesticides that are of a concern. Pesticides are organics again most of the time, but they have either a chlorinated solvent, they either have a chlorine or fluorine or something that's causes very similar to a disinfectant behavior in drinking water, basically. So you want to use that molecule to essentially disrupt the normal human body, normal body function of whatever you want to kill. So chlorines and fluorines, especially TCE, the chloride, organochlorines are all man-made or what are called xenobiotics. So they tend to, most animals are not used to seeing these compounds. So when they get hit with a lot of them at very small, in a very short period of time, their body doesn't know what to do with it, and it causes genetic mismatch or some affects their DNA and then eventually kills them. So that's the idea behind pesticides. Of course, if we consume them in small quantities, same thing will happen to our cells, and we could have issues too. So we do worry about pesticides. They're extremely insoluble. A lot of them tend to be very, very, very insoluble and tend to be very hydrophobic. So if they do get a chance, they will get into a solid phase or into organic matter. Okay, which means if it's in water and you drink it, you're giving a lot of organic matter, for it to get into, and it'll get into it, So one of the things about pesticides is usually they are very large size molecules, and they have chlorines or things that are very non-reactive, so they tend to persist. Okay, so DDT was banned in the U.S. in 1970s. We still can detect DDT in some of the soils. Okay? Of course, we blame Mexico and others, and say that it all came from there. But quite honestly, there is, it's like DDT's half-life is like 50, 60 years. So if you had high concentrations, only about half of it is gone. It's still there. So when did India ban DDT? Or is it banned in India? Yes. When? Yeah, DDT is banned by WHO. But there are a few countries that asked for an exception. Actually, in 90s, WHO banned DDT and said you should stop DDT production worldwide. Mexico, India, and few other countries basically came out and said, no, we will ban it on agriculture use, but we will not ban it for vector control, which is to kill mosquitoes. So there were countries in Africa, there were countries in India was one of them, in Asia, and then a few countries in Latin America. They said that they'll continue to use DDT, but just for vector control. There was still no production of DDT, but UN allowed it and said, there is warehouse of DDTs, there is DDT sitting all over. As long as you don't use it on fertilizers, you can use it for vector control or for mosquito control, because it's very effective for killing mosquitoes. That was back in World War II. Soldiers they would throw DDT on the soldiers, they would basically dump them with like powder. They would put DDT on your face and stuff because the mosquitoes won't kill you, especially those fighting in Vietnam and areas where there is a lot of jungles. They would just be put. They would use DDT like face powder and go into the war zone, and then there are some very, very serious complications. A lot of people who went through that battles ended up getting cancer because of what DDT did. It just stayed in their body and just ruined their DNA over time, and disrupted their cell repairs and things like that. So those are some of the contaminants. So the contaminants, so we don't know what contaminants usually are there at the site. So we tend to do a broad sweep. And then sometimes it's guided by what kind of industrial activities took place at the site or what happened. But sometimes we may not say what kind of chemicals were used, because industries don't tell us what chemicals are being used, or they are not required by law to report it. So we tend to run a lot more than what it is. So it's also important to collect samples, both groundwater and soil samples, up dip of the contamination, because then you can say what the chemistry looked like near your, your outside of your contaminated area, and what does it look like inside of your contaminated area. And the ones that you collect up dip, where we think there is no contamination, that usually becomes the standard for cleanup. So we say we have to at least clean up to that level, because had there been no contamination, that's how the site would have looked, or that's the level of contamination there is. So and the way we collect samples also plays a very big role in terms of what your chemistry looks like when you analyze it. So it's very, very important that you collect samples correctly, and you collect samples with the right frequency, so that you can detect the changes. Historically, in groundwater, when it comes to groundwater, so we need a well to collect our sample, right? So we have a well, it's screened, and it's sitting in the aquifer. There is water in the well. Okay? We really don't want to sample the water in the well. What we are interested in is sampling the water that's in the aquifer, not the water that's sitting in the well, because the water that's sitting in the well is exposed to atmosphere, whereas the water that's in the aquifer is not exposed to atmosphere. The water in the well is hitting plastic. The water in the aquifer is hitting sand grains. Okay, so obviously the chemistry is going to be very different between what's in the well versus what's in the aquifer. So we have to remove the water in the well and get the water in the aquifer, and then start sampling that aquifer. Okay. What we used to do in the past is we would do what's called as 3 well volumes. We would purge out 3 well volumes, okay, because the well is not simply a well. What you do is you make a bigger hole, put your well, but you also put some sand around it, so that you get a good connection between the aquifer and the well. So your well might be just a few inches in diameter, but your hole is probably in tens of inches in diameter, so it's slightly bigger hole. So wherever you have the hole, you have disturbed the soil, so it's not really the aquifer. So to kind of get rid of that, what we used to do is we would remove 3 well volumes. Okay, so we would purge out. So we have a well. Let's say that well is 100 meters, and it's of let's say 30 centimeters, or 0.3 meters in diameter. So we would get the cross-sectional area, pi d squared by 4, multiplied times 100. We would get the volume of, and then if the water table is at, let's say, 20 meters below sea levels, we would multiply times 80, because there is 20 feet nothing there in that well, and we would multiply times 3 and remove that much amount of water out before we take a sample. Okay. This practice still goes on in some places. What is the problem with this practice? Water waste. How much water are you wasting? Well, it's 100 meters times pi times 0.3 times 0.3 divided by 4 times 3, so not a whole lot of water. Okay, a few hundred liters, probably 50 liters, 100 liters, okay, a few hundred liters. It's a lot of water, no doubt, but that is the price we pay for getting a good sample, right? We really cannot sample the well. I mean, that's not telling us what's in the aquifer. Okay, so chances are that well water is contaminated, so we'll have to store that water. And if you want to be so water conscious, after you take the sample, dump the water back into the well, and you haven't really wasted any water. And it happens at some places. Some places it's not allowed. But what is the problem with this type of sampling? So what we are doing is we have a well. We are pumping 3 well volumes, and then the water flows into the well. Obviously, if you pump the water is being replenished in the well. So we have a flow rate Q, and we know what the volume is, and you say, okay, I pumped for so much time, I've removed 3 well volumes, right? and I take a sample. Okay. Good, bad? Is there an issue with it? So here's my well. This is the portion where it's screened. Usually there is like a gravel pack sitting. This is called the gravel pack. Okay, this is high permeability material basically. This is your screen. Okay. Let's say my water table is here. Okay. So what I do is, this is my length L of water in the well, and I know the diameter of the well D. Is the volume that I would remove, okay, is the volume that I want to pump out. If I know the pumping rate Q, okay, Q delta T should be equal to and I can calculate my delta T and get my sample. Okay. So, what is good about this? What's bad about this? Right. So, you are convinced that I've removed not just the water from the well, probably I've removed some of the water from this area. So, I'm getting a truly a sample from the aquifer as opposed to getting a sample from in the well, okay? Because the water in the well's chemistry is going to be very different from the chemistry in the aquifer surrounding it. And we want to see what's happening in the aquifer. We don't want to know what's happening in the well. So it does provide that, okay? But any cons, any problems with it? Expensive? Monitoring is always expensive. That's, but we have to do it. There is no other way to know whether there's contamination or not. Okay?
If the radius of influence is closer, so the representative area might be few meters and hundreds of meters.
Right. So basically, for making my cone of influence very large, my Q has to go up. The more I pump, the more the water will come from a larger portion of the aquifer. So if I have a little bitty contamination here and my area of influence is this, what happens is I'll end up diluting, I'll get a very dilute sample, and that may not be representative. Okay. So of course, if Q goes up, delta T goes down because this side is constant. So your sample comes out very quickly, okay? Which is good, right? We can take a sample and go home and not worry about being at the well too long. But the downside is if we pump at very high rates, what we also end up doing is we create turbulence right around this well. So the water here is laminar, but when it hits the well screen, there is a very, very small opening, okay? So overall the flow is Q, but over an individual piece the velocity is very, very high, like, because the screen size is very, very small, okay? So because your velocity is high, you get highly turbulent flow right around the well when you pump. When you get turbulence, you get mixing, and so the water is coming with a fairly high energy and it's being mixed, so it will start exchanging oxygen with the atmosphere that's in the well. Okay. And you will end up getting an oxidized sample. Okay. So you may be in the aquifer, it might be chrome 3, but you have just oxidized it to chrome 6. Now you're saying, like, this well is contaminated. Okay. There could be other things where things like benzene and things like hydrophobic organic contaminants, which are very reactive, so that much oxygen might be enough for microbial degradation of it, or like some of it might just volatilize because you're adding air to it, like or mixing it with air. So as a result, you will end up degassing a lot of some of the organic contaminants, especially the ones that are volatile. So you will end up altering the chemistry, or you will end up losing some of the contaminant mass. So if you're doing something like total dissolved solids, and the other thing is, if you have a very small pocket of contaminant, you have sampled over a much larger area of your aquifer, and it might end up getting diluted, like so there could be dilution effects. So if you're looking at some very traditional contaminants like total dissolved solids or things like that, it's okay to do this 3 well volume approach, but generally speaking, we don't do this. What we do is we put a tube and put a pump, what's called as a low flow pump. Okay. And by low flow, it's usually about less than 100 mils an hour. Okay. So you're pumping it like about 1 to 2 mils a minute. Okay, very, very low flow. And what you do is when the water comes out, you tend to take pH, specific conductance, EC, redox, those kinds of measurements. And once that stabilizes, that's when you collect the sample and take the sample. Okay. Much slower process because you're not pumping at a very high flow rate, but you will get a very undisturbed sample because that level of pumping will not cause turbulence right at this screen. The downside of this is it will take a long time for you to collect the sample. It takes so typically at a contaminated site, geologists may get like 2 samples a day, like 3 samples a day, so it slows down the process, and or you have to hire more people to collect this, but nonetheless it gives you a much more representative sample of what's in the aquifer. And the other thing we want to do is if we have chemicals that are volatile or that can are organic, we don't want, what is the best type of container to collect that sample? Would you use a plastic container to get organic contaminants? Stainless steel would be good. What about metals? Metals? You don't want to put glass because glass is silica. So some of the metals may actually sorb onto silica, so. Or high density polyethylene. And then if that chemical is reactive to sun, we want to collect it in dark colored bottles as opposed to white bottles. So those are called amber colored bottles. And the second thing is when you collect volatiles, okay, usually we do what's called a zero headspace. Sample, and the zero headspace sample was, back in the day, we would essentially take a chamber, okay, and connect it to nitrogen, okay, and purge it with nitrogen, and we would remove all the oxygen that's in this chamber, okay, and then we would take the sample and fill it in this, okay, and fill it to the very brim and close it, okay, and then we would pull the sample out once it's closed, so we would close it in the chamber and then pull it out and then store it. That way it's not exposed to oxygen at all. Okay, so these days we get what are called Peddler bags, and these are basically bags that lay flat, and they've got a syringe, and you can actually pump water into it, and it's like a balloon. So as the water goes in, it starts to it starts to inflate, and you get a sample. The good news is there's no oxygen, there's no air to begin with, so the bag is under vacuum, and once the first drop of water comes in, the vacuum, we open the bag so that only the water goes in. There is no air being exchanged in it, so it just fills up. So Peddler bags are made up of organic material, and they tend to be but they tend to be very inert, because inside they are coated with Teflon, so that the water only comes in contact with the Teflon and not the plastic. But they tend to inflate like a balloon, and only thing is, if they are made up of a material that's much better than the balloons, so that when they inflate, they don't cause, the material stays rigid so that it doesn't cause punctures, or for the water to come in or escape, or air to come in and escape. So sampling, we spend a lot of time and a lot of money trying to get samples. Some agencies in the US require you to use stainless steel for your well, which means this entire well is built with stainless steel, because if it's built with polyethylene and then I have water coming out of this well, it will come into contact with it may get into that and not get, it may get out of the water and get into the organic high density polyethylene, and then that may cause a sample that underestimates how much contamination is there. So there's a lot of time and money spent collecting samples. So once we collect samples, the next thing we want to do is we want to make sure that it is not exposed to the atmosphere, because we want to preserve what it looked like in here, so that's where the sample should be. So we tend to put them in ice chests, we close it. We have what are called as field blanks and trip blanks. This is deionized water that we take to the field, and we open and expose it in the field once, and then we expose it while we are traveling in the car or whatever in the truck, because the trucks give out exhaust, so they have there is contamination that could, you could get contamination just because your sample is sitting in a truck being exposed to some diesel or some diesel exhaust or something like that. So the field blank, the trip blank, is what we open when we are traveling, and if there are any contaminants, they will go into that blank, and that will tell us whether we transported this sample correctly or not, over time. And then there are something known as holding time, which means you can only hold your sample for a certain period of time before you analyze it. So for most organics, that tends to be within 24 hours. Okay, so when you do a field sampling, your lab better be ready to take your samples, because you have less than 24 hours to get your sample there, and then if the sample doesn't make it on time, we've basically spent a lot of money collecting a sample that we can't analyze, or we can't report the result. So field sampling, quite a challenge. And then when you do field sampling, invariably you forget something, and then so you have to improvise in the field. If you forget the pump, then you're in big trouble. You can't take your samples. So it requires a lot of planning, a lot of very careful planning, and then preserving the sample and transporting the sample is just as important as collecting the sample, because collecting your sample is just one piece of that puzzle. If you transport it incorrectly, and if you let it sit in the lab for too long a period of time, your analysis is going to be just not right. Okay. So part of the site investigation is to map out these logistics and make sure that your lab is ready to take your samples, and your people in the field know that you're coming to collect samples, okay? And so there are no surprises, especially with groundwater. A lot of these wells happen to be on people's property because it's a private, there are very few wells on government lands. So you have to go to somebody's house and collect a sample. And if they're not at the house or they don't want to let you into their house, you will not get a sample. Okay. So I had a student. I've always told my students, call people, only then you go. You don't go without calling because they may not be home or they don't know what it is. It's risky. So my student went collecting samples, and so he went to one of the sites. He didn't call, so it was closed, and he knew that he would get a lecture from me when he came back, obviously, because I told him not to do it. So instead he says, hey, I'll just go to the next house, and I have sampled there before, so it's more a residential neighborhood, whereas this one was a farm, so nobody was at the farm, but I'll just go to the residential neighborhood and collect a sample because I'm already here, right? Turns out he drove into this residential neighborhood it was like about 7 in the night, so it was a little dark. It was winter, so it was dark, and there were kids playing. He parks his car and gets out, so one of the kids don't know who he is, so runs into the house and says there's a stranger, and then a man comes out with a gun and ready to shoot my student. Of course he sees that there was Texas Tech written all over his truck, and he kind of the man knows him because he's been there and sampled before. So quickly the man is trying to hide his gun and say I didn't know who it was, and obviously he wanted to protect his child, so my student almost got shot, but luckily we got some good samples out of it. So the story has a happy ending. There was nothing, no one was harmed, but it's extremely dangerous sometimes. When if your logistics are not correct. I mean, if you had called this person before he went, the whole incident could have been avoided. But sometimes students have to live and learn, or if they don't learn, they may not live. That's the moral of the story. But anyway, the student was trying to do this to avoid a lecture from me, and ended up getting a bigger lecture from me because of this whole thing. So that's that. Anyway, so the second part, once we get the chemistry, is also to do the geologic characterization. So what we want here is we want to know what the geology looks like, both in the vertical direction and in the horizontal direction. Okay, a lot of times you get geological maps, which will tell you what it is in the horizontal direction, the aerial direction, the aerial plane, but it doesn't quite tell you what's happening in the horizontal plane. Okay, so of course, collecting that data is pretty expensive. Okay, a typical well where I live in Texas, it's about $50 to $80 per foot of drilling. So if you want to drill 1 feet, it's about $50 to $80, depending on how many wells you put, what kind of material you have. That is till you hit 300 feet, 400 feet, in that range. Okay, once you go past 300 feet to about 600 feet, the price goes up by it almost doubles. Okay, so now it's like $100 to $120 per foot there, and if you go past 600 feet, you almost get into this $1,000 per foot, or $500 per foot, because the technology to drill changes, and your drill bits are encountering much more overburden pressure. So if you you have to have a very good material drill bit to make sure that it can cut through and maintain the pressure. So the price of drilling goes on exponentially up when you start putting wells. Okay, so it's very important that every well that we put, we make a record of what the vertical profile looks like. Okay, so there are 2 things that we do. One is what's called as the drillers pull out the cuttings, like, so they're drilling, and when the drill goes down, they're actually putting some drilling mud or drilling fluid to keep the lubrication, and then they're just drilling, drilling, drilling. So they, after a while, they stop. Every 10 feet or so, they stop. They collect a sample. Okay, they pull the sample out, lay it on the ground, pull it out, lay it on the ground, pull it out, lay it on the ground. So every 10 feet sections, the samples are laid on the ground, and then they'll let all that water, that drilling fluid, and the drilling mud to evaporate. Usually those are clays. Those are very fine clays, clay slurry. So we let it evaporate, and then the drillers usually get a feel and say, okay, this is sand, this is clay, like, based on the feel of it. In some more expensive projects where we are doing very deep drilling, we take those samples and send it for sieve analysis, and then we do sieve analysis on it. Of course, we have to wash out all the drilling mud before we do the sieve analysis. The second type of logging that we do is we put a geophysical log, and we measure either current, voltage, or which are an indicator of how well the water moves. Like, if you have a lot of water, water conducts electricity. Clays don't, so you can kind of use the voltage differences to find out how much water is moving or whether there is a potential for water. You can also correlate current movement to conductivity, because conductivity is the ability of ions to, like, conduct electricity. So if I'm conducting a lot of electricity, I know I have ions in that water that are conducive to movement, like, so we can tell whether the water is brackish or salty or, like, fresh, based on some of these geophysical logs. Again, geophysical logs are extremely expensive. A shallow logging, which is under 500 feet, will cost anywhere between $5,000 to $6,000. If you want to do deep logging, you need more specialized equipment, and the price goes to like $20,000 to $25,000, sometimes $30,000, depending on where you are. And but nonetheless, like, keeping that information is very important. In U.S., every state, almost every state, I don't know of a single state which does not require the drillers, like, so to submit a drilling log to the state. Okay, so there is the water agency in the state. In our case, we have the Texas Commission for Environmental Quality, and anytime there is a well drilled, the drillers have to at least estimate whether it was sand, silt, or clay, or whatever the material is, mostly by visual inspection. They don't have to do a grain size, or they don't have to do geophysical logging, but at a minimum they have to be able to tell, okay, this was clay, or it looked like clay, this looks like sand, whatever, and then plot that drilling log and send that drilling log to the state, okay, a copy of the drilling log. And as a matter of fact, many states, Texas has put that information on a website, so you can actually go click on a point and it will show you what the drilling log looks like. Some of these wells are very old wells. They were drilled in 50s, 60s. Some of these wells are new wells, but it's almost a requirement now to keep that drilling log. So that is one form of crowdsourcing for your information, because somebody is drilling a well, you might as well get that information, because it costs a lot of money to get that information. And if it's sitting with somebody private, it doesn't help the next investigation. So we go, when we do contaminate, before we go and do any drilling, we actually go to the logs in that area and say, what logs are available. And then if you have these types of logs, we start looking and saying, okay, the water table is here, there's sand here and here, so very likely there's going to be sand here. So we start building that geologic conceptual model based on data that's already available. Okay? But we still have to drill. There is absolutely no recourse for us in groundwater other than drill and see what's actually happening. Like, if you want to collect a sample, you have to drill. One of the other good things about drilling logs these days is post 2006 especially, the states require us to put a GPS coordinates on it. Like, before, the state would have a grid and grid number, and it would tell based on which grid you had to report which grid you were in, and you could approximately tell where that well was. But now, drillers have to carry a GPS, and then they'll tell you the well is exactly on this location, so we can actually map it and see what the well looked like. And it also tells us where are the nearby wells. Okay, where is the up dip well? Is there a well there already? Is that well good enough for me to go use it for the sampling that I want to do? And then it becomes a question of, will that person allow me to get a sample? So that's what we do. So we get a lot of information from driller logs. If it's very shallow surface, we use augers, hand augers. In some places, anytime we drill, we have to call a number, a toll-free number called 1-800-DIG-SAFE, and tell them that we are going to drill a well here, and give approximate location of where we want to drill, and they'll tell us that these days you can do this electronically too, but back in the day you had to call that number and give the location, and they would come back and give a report and say, where is the water? Is there a water line? Is there a sewer line? Is there an oil and gas pipeline? Is there any electricity lines buried? So they would give information and say, oh, you want to drill at this location, but you will be cutting right through a water treatment sewer line, and that's not allowed. So move or do something So it kind of gives. So there are records of where the water lines are, sewer lines are, and all that stuff. They just don't want that information to be public because people can use that for acts of terror, terrorism. So they tend not to disclose where it is, but you can call them before you have to call them. You are required by law to call them so that they can tell you, don't drill there, or it's safe to drill there. And then once you have that permit, only then you can go drill. And then usually we drill the first few feet with a hand auger. The reason for that is if there is a pipe buried or if something has happened, if you start just using a mechanical drill, it will just drill right through it, so there is no way to stop it. Whereas if we hand auger the first few feet, if we hit something, we'll just stop and we'll say we don't want to do anything, we don't want to go any further. So it's a protection or a safety mechanism for us to avoid damaging existing infrastructure. So when we drill, we just do hand augering, and it's painful. If you've ever used a hand auger, you'll build. If you do that for a regular basis, you will have very good muscles in your hands, but it is tough to cut through. But so usually we cut the cement off with a mechanical. We cut through the road, make a little hole, and then once we go a few inches, when we have cut the concrete, we just go and do a hand auger, So the other thing that's done quite a bit in contaminated sites are what are called this cone penetration test or a cone penetrometer test. And what that cone penetrometer test does is essentially drill a cone, or drill a hole, and then the resistance with which that tip moves is measured, and that resistance is an indicator of what type of soil you have. So if the cone just pushes itself through, obviously you have clays or very soft material, and if you are trying to push it through a sand or a gravel, it tends to exert a greater resistance. So what the cone penetrometer does is it kind of measures that resistance and gives you a fairly good vertical profile with very little damage at the site. One of the advantages of cone penetrometer testing at contaminated sites is if you drill at a contaminated site, all the sediments that are coming out are contaminated. So you have to make sure that you have collected all the sediments and then dispose it off properly. So what RECRA says is you are now the owner of this contamination, so we'll hold you responsible for having that contaminated material unless you put it in the landfill or incinerate it or do whatever it is. So unless you eventually get rid of it in the grave, you are held responsible for it. So at a lot of contaminated sites, drillers don't want to drill unless they are very sure that somebody else is going to take that contamination. What cone penetrometer test does is you're not drilling, you're kind of drilling, but you're not extracting any material out. And because you're not extracting any material out, you can get a profile without really having to pull out any contaminated sediment onto the surface. Like, so everything is left in place. There's a little bit of a damage because you're still punching through the ground, but it's a very minimally, what we call as a minimally invasive test. Works very well as long as your depths are below 100 meters. If you want to go and look at things above 100 meters, cone penetrometer doesn't work. I mean, it encounters too much overburden pressure that it just gives you very bad readings. Like, but for shallow contamination, CPT is really a very, very fast and convenient method to use. The other thing that happened, another technology that has come up is when we drill the wells, as I said, we want to first drill the hole, right? And then we put the well. The way we drill the well is we have a drill bit and we basically make that drill bit go down. Like, so there are two methods. One is what's called as a percussion method, where we just hammer it with a hammer. So there's a hammer like action, like, and it goes up and down, and we keep on hammering the drill bit down. Okay, and as the drill bit moves, it keeps rotating. And then there is other called the rotary drilling. With the rotary drilling, what we do is we basically rotate the drill bit, and the cutting action, that is cutting and grinding action, as it goes down, and it creates. Okay, the percussion method is used for shallow wells because you can hammer through. The rotary method is needed if you're going through consolidated deposits like, sandstone or stone and other things like that. The rotary method doesn't work very well in sands because as you crush, the sand will just keep falling into it, so it doesn't really work. So you have to use the percussion method. But still, because you're drilling, you have to you're encountering friction. To avoid that friction, you have to put drilling fluid or drilling mud. Okay, so the drilling mud or drilling fluid is essentially a viscous material, usually clay, foam, or something like that. And what it does is, as the drill bit moves, you keep on adding water to it or this foam to it to keep it lubricated. Otherwise you'll get a lot of friction pressure because it's moving in this direction, and as it shears through, it'll get sheared. Like, but all that water, if you're into a contaminated site, will be contaminated, and now you have to dispose that properly. So there is a big push to go towards fluid-free drilling methods. Okay, so where you don't either, if you have a contamination that's in water, you say, okay, I don't need. I'm not going to put water, but I'm going to put like air or something like that. So pneumatic drilling is one technique, pretty expensive. The other one is to say just do fluid-free techniques, like, So one technology that has come out is what's called as a truck-mounted geoprobe. So I'm showing you a picture of that, and what it does is, so this is you can drive this into the field, and you say I want to drill a well here, so you set it up, and essentially this goes all the way up and falls down. Okay, so it's like a hammer. So you're just hammering that well down. Okay, there is no fluid to keep it. You can put wells to about 100 feet, about 30 meters, 50 meters, fairly easily with this technique. Okay, and you can put like 2 or 3 wells in a day because it goes fairly fast. So if you're doing shallow groundwater sampling, or if you want to put shallow wells, especially at contaminated sites, we make use of geoprobe quite a bit. This is what's called as a truck-mounted geoprobe because it's mounted on a truck. You can also get a handheld geoprobe where you actually drill the well by holding it in the hand. A little bit more difficult because your body is taking up all the resistance because you're holding it, so you will feel it after a while. But the truck-mounted works very well for at contaminated sites because you have no other fluids attached to it. So there is no more cross-contamination. There is no contamination associated with that you have to dispose of. So you can put a well, So we can typically put about 2 or 3 wells in a day at a contaminated site because especially the contamination is fairly shallow. If it's a very deep contaminated site, this will not work. You will have to go to conventional drilling, which is expensive, and if you want to do it at a contaminated site, it gets even more expensive because of the liability associated with that contaminant. Hydrologic characterization. So to do the hydrologic characterization, we install a set of piezometers or mini wells, and those piezometers tell us what the heads are, what the gradients are, which side the flow is taking place, how is the contaminant likely to move. Okay, so in a hydrogeologic characterization or in hydraulic characterization, there are 2 aspects that are of interest to us. The first aspect is knowing what is the direction of the flow, and the second aspect that's of interest to us is the hydraulic conductivity, the rate of movement of water. Okay. So we want to get these 2 values from the field. Okay. To get the flow direction, how do we get the gradient? Because if you have these 2 pieces of information, we can use Darcy's law, right? Everybody knows what Darcy's law is. Yes, no, maybe? What's Darcy's law?
The flux is directly proportional to the gradient.
Which flux? Hydraulic flux, volumetric flux? Volumetric flux, okay. So what do you know about Henry Darcy? Who was this Henry Darcy guy? What's with this Darcy's law? He was an engineer.
Just working with water supply systems.
Uh-huh. So Henry Darcy was a civil engineer, so all civil engineers in this room can be proud that groundwater hydrology came out of civil engineering, okay? And he was working in a place called Dijon, France, okay? So those of you who know, Dijon is a place where they grow a lot of mustard. Actually, you can buy Dijon mustard, which is a fairly expensive variety of mustard. And the city of Dijon was running out of water. They were on surface water and they were running out of water. So Darcy was a young engineer. He was, I think, in his 30s, like 37 or something like that. Like, he was a fairly young engineer, and he was told that there are some springs outside of the city of Dijon, like somewhere a few miles away from Dijon. There were springs, which means they knew that there was groundwater there, and he was tasked with bringing that water to the city. Okay, that was his task. Okay, and it was a little bit surprising, right? In France, which was at that time a fairly conservative society, like to think that a young engineer would be given a task of doing this, like seemed odd, but turns out a lot of engineers didn't want to take that job because they didn't know any theory. They had no idea what it was. All they know was there were springs. I have to bring water. Okay, there was absolutely no theory to say how water would flow. They didn't want to construct any. There was no way to pump this water. There were no pumps. So a lot of senior engineers knew better. They said, "I'm not going to take this. It's a very risky project." But young Darcy had no choice. He was given the project and he took it, and he said, "Okay, I need to move this water from the springs locations where I know there is water to my city. How do I do it? How does this water move to the city?" So he did some experiments which are now called that led to the famous Darcy's law. What he did was he took a column and filled it with sand from that area, and he had a little tap here, and he had a reservoir up on the top, and kept the water constant. Okay. So this was the length of the tank, right? And this was essentially the pressure head up on the tank. Here the pressure was atmospheric. Okay. And what he did was he varied the flow rates, okay, and by basically making this reservoir longer or shorter, like, so he said, I'm going to apply more pressure, so there'll be more flow coming in, because all this pressure head will be converted to some kinetic energy at this point, and Q over A, and it'll start flowing down. Okay. So what he found was, he said that the flow rate Q was proportional to the area of cross section, and when he made a bigger pipe, he got more flow. When he made the lesser pipe, he got the same flow, and he also got flow rate Q is proportional to the hydraulic gradient. Okay. What's that? Well, so why negative of hydraulic gradient? Correct. So the negative sign simply implies that your flow is in the opposite direction of your hydraulic gradient, like, so Q is proportional to A dH over dL. Of course, let's not forget the negative sign. So Q is equal to K A dl. So I'm going to write it as the derivative in the derivative form as dH over dl. Okay. So this is the famous Darcy's law. Q over A is what? Oh my God, the undergraduate education really kills us. Okay. Q over A immediately becomes velocity. Okay. All over the world, I ask the students, what's Q over A? They're like, velocity, like, No, it's a flux. Okay. We talked about it in the first class. Okay. And why is it? I'll just tell you why we shouldn't call this a velocity. Okay. So this Q over A is called what in groundwater hydrology? It's not called velocity. It's called specific discharge. Okay. And this K, what is this K? Okay, so turns out this K, when Darcy did this experiment, he did this in water because he was a good civil engineer and all he cared about was water. A few years later, there was an American physicist called Buckingham who actually took Darcy's law and said, I'm going to use this to study the movement of petroleum in subsurface. Okay. And what he found out was he was interested in seeing how oil and petroleum, crude oil would flow through subsurface. And for him, the crude oil was not consistent. It didn't have a constant density. It didn't have constant viscosity because crudes can be different based on different locations, how they are formed, So what he found out was this K really is not a constant like we think, but the K can be written as little k rho g over mu. Okay. This is called intrinsic permeability. Okay. And this is density. And what is mu? Dynamic viscosity. Okay. And this has units of Newton second per meter. Okay. Think about it, okay? So this rho g term is also called what? Specific weight, okay? It's specific gravity if I divide it by density of water. So if it's anything, it's just specific weight. And if I take this mu divided by specific weight, I get what? I get the kinematic viscosity, okay? So you can write it. But this intrinsic permeability is measured in meters squared or centimeters squared or whatnot. In petroleum engineering, it's very common to use Darcy, okay? So in honor of the great civil engineer who gave us Darcy's law, but what this K is a function of both the, this is based on geology, rest of these are based on fluid properties. So depending on your fluid, you can apply Darcy's law except that the fluid properties and the geologic properties have to be accounted for in this hydraulic conductivity. Okay. What is this hydraulic conductivity? How do we define this hydraulic conductivity? It's a property of the soil and the fluid. Okay. So the easiest way to define hydraulic conductivity is to go to this definition and say it is the specific discharge per unit gradient. If I make this gradient 1, then the discharge associated with it, the specific discharge is the unit gradient. Okay. What you need to understand in this whole derivation is that hydraulic conductivity, right, is a constant of proportionality. Darcy never measured hydraulic conductivity. Okay. He could have calculated it, but he did not change hydraulic conductivity as part of his experimental design. Okay. What he changed was cross-sectional area, what he changed was gradient. Okay. And what he found was, since these two relationships held, to mathematically write that equation, he had to put a constant of proportionality. And that constant of proportionality is hydraulic conductivity. In other words, what it means is that you cannot measure hydraulic conductivity in the field directly. I can measure area directly, I can measure hydraulic head directly, I can measure the length directly, so I can calculate this because I can measure this, and I can measure this. Of course, to kind of measure this, I need to know some length and width and some geometry, but these are all things that I can measure in the field. This is not measurable in the field directly. In other words, I don't have an instrument that I can go and put and say that's my hydraulic conductivity. Hydraulic conductivity can be backed out if I know Q, if I know A, if I know the gradient. Okay. But there is no measurement per se that you can get. Okay. And if we look at the porous media, okay, it's made up of a lot of different grain sizes, right? So when Darcy was measuring, he was putting sands in it. Of course, you know, sands in Dijon at that time was fairly uniform. He was working with a relatively uniform material, but that doesn't mean that every grain size was the same, exactly the same. There were some bigger grain sizes, there were some smaller grain sizes. That's just the way the weathering process works, and that's how the geology heterogeneity is formed. Okay. So when he measured this hydraulic conductivity, that hydraulic conductivity was a function of, our fluid was the same, so we don't worry about fluid properties. For us, it's water. The density of water and viscosity of water don't change as much. Okay, they change a little bit with temperature, but within the normal ranges of what we see, it doesn't change much. Okay, so water, that's why, is an incompressible fluid and works great for us. Okay, but this K does change with the geology. Okay? But even if I take a column, a sand column, right? That sand column is going to have multiple pore sizes. The reason it will have multiple pore sizes is because there are multiple grain sizes, and the arrangement of those grains is what forms pores. Okay? So, but I have only one hydraulic conductivity value. Okay? Darcy did this experiment. He knew the flow rate, he knew the A, he knew the gradient because he was measuring all of that in his experiment, and he was able to back out this K and said this is my hydraulic conductivity. But what's important to recognize is that that hydraulic conductivity, as we just said, is a measure of how easily water moves through our system, right? Higher the specific discharge, the more faster the water will move because it's a velocity like term. It's not velocity, but it has got very similar characters. It's a flux. Okay? So greater the flux, more is the water movement, and if I control my gradient, the greater the flux, the greater is your hydraulic conductivity. Okay? The smaller the flux, smaller the hydraulic conductivity for a given gradient. Okay? But even in his sand column, there was a range of grain sizes, right? So that, but he has only one hydraulic conductivity. He doesn't have a range of hydraulic conductivities. In other words, the water in the smaller pore is moving a little bit faster versus the water in the larger pore, because of the cross-sectional area, is moving a little bit slower. Okay. So if I go down, if Darcy was able to go down and look at individual pores of varying sizes, right, he would see that the range would be, the flow rates would be very different in each of these pores. Okay. Some flow paths are going to go, and then there are some other flow paths which are a little bit more straightforward, and they're going to go. Okay. So when we measure a flux, what we are saying is we are averaging over a cross-sectional area A. That cross-sectional area, portion of that cross-sectional area is occupied by pores, and portion of that cross-sectional area is occupied by sands. Okay, the porosity gives us the ratio. It tells us how much pores are there versus how much sands are there. Okay, so when I take this A, I'm averaging over both the pores and the sand grains. Okay. In reality, the water is only moving through the pores. Right? So the velocity with which the water moves is different from the flux or the specific discharge I'm calculating, because the water is only moving through pore space, whereas the flux is being calculated over the entire cross-sectional area. Okay. As a matter of fact, if we call this little q, as it's conventionally called, our average linear velocity is q over n. N is your porosity. Okay, because the porosity gives us the fraction of, for a unit length, for a, in the volume, if you just look at the area and take a unit height, okay, what it's telling us is, the porosity tells you this is the fraction of void space, and the water is only moving through the void space. So whereas the specific discharge is the water that's moving over the entire, averaged over the entire space. Okay. So the velocity is, we have to divide this by porosity. Turns out in open channels or in pipe flows, where we first learn Q over A is equal to V, our porosity is equal to what? Porosity is equal to 1 because the void space is exactly the same as my total volume. As a result, Q is equal to velocity. But in groundwater, Q is not equal to velocity because when we do Q specific discharge, we average over the entire cross section, whereas the water is only moving through the pores. So if at all you want to talk about velocity, that velocity has to be just over the pores. Now there's another kicker, right? So we have pores, and we just said that even in a simple sand column of Henry Darcy, the pores have different sizes. Okay? Which means if I look at the velocity of this flow path, it will have one velocity. If I look at velocity in another flow path, it's going to have another velocity. If I look at in another pore, it will have another velocity. Okay? So that is what's called as pore water velocity. Okay? That is the velocity at individual pore. A lot of times we cannot measure at that individual pore level because we don't know what the pores are, what they look like. All we can measure is an average velocity over the entire pores. So when we divide by porosity, we call that the average velocity or the average linear velocity. The reason for that is we are averaging over all the pores in that cross section, all the pore sizes in that cross section. So the water is moving at different velocities to get to that point. Okay? One is moving at one velocity, one's moving at another velocity, another velocity, another velocity, but we are just taking an average. Okay? Very similar to pipe flow, but a little bit more dramatic, because in a pipe flow, what's the velocity here? 0. Why? What's that condition called? So there's a no slip boundary condition there, which gives the velocity. The velocity is maximum here. Why? Because virtually there is no friction. It's surrounded by water, so you will get. But if I take Q is equal to AV, I'm getting an average velocity through my pipe. If I measure the velocity here, it will be 0. If I were to measure the velocity here, it will be maximum, it will be some other value. If I measure it here, it will be some other value. So if you are able to measure velocity across that profile, you will get a velocity profile that looks like this. But if I say, here's the Q coming, divide by A, what I get is a velocity which is an average velocity. Okay? For all engineering purposes, that average velocity is good enough for us. We don't need to really see what the profile looks like. Okay? So we don't really care. The same thing here, by dividing it by porosity, I'm dividing over all the range of pore sizes. So this is called the average linear velocity, okay, on average. But if I look at this pore, if I look at any cross section, this pore, if it's very small, the water will be moving much faster. If I have a pore that's larger, the water will be moving a little slower. Okay? And so there is a range of velocities that are happening across this, but I can only talk about velocity only when I'm looking at the pores, not when I'm looking over the entire cross section. What Darcy velocity does is it looks over the entire cross section. Okay? So what it also means that this K, right, is an average property, because we are saying that this Q over A is some average specific discharge, which makes this K an average property too. Okay? Can we measure an average? If I want to know what is the average grade of in this class, okay, can I measure it? No, I have to measure I have to know individual persons' grades. sum it up, divide by the total number of people, only then I'll get. There is no way I can go and measure the average directly, which again is another way of saying that hydraulic conductivity is a purely figment of our imagination. It's an average behavior. It represents the average flow behavior in our aquifer. Since it represents the average flow behavior, there is absolutely no way for us to measure it directly. You cannot create an instrument that you can put in the ground and say that's my hydraulic conductivity. Simply not possible. If you can do that, you can also measure the average in this class. The day you can do that, the day you can measure average of this class. Okay, it's physically impossible. But what we have to do is we have to measure this side, we have to measure this side, and we can estimate this. So when we go and measure hydraulic conductivity in the field, when people say I went to a hydraulic field, did a pumping test and measured hydraulic conductivity, what they're actually doing is they're estimating hydraulic conductivity by measuring both y and x. Okay. So if I have an equation mx plus b, right? If I know m, I can estimate y. If I don't know m, what do? I have to measure x and y, draw a straight line and get the slope, and then that is what's called as an inverse problem. The inverse problem means in a forward problem, what do? Is we know our inputs, we have a model, we get our output. In an inverse problem, we use the output to estimate input, run the model backwards. So that's what we have to do to solve this problem. Okay. Gradients we can measure directly. Okay. So how do we measure? What is gradient? Again, first time we encounter gradients in fluids is probably in your open channels, right? Or somewhere in hydrology we talk about gradients. What's a gradient? So I have a surface, okay, land surface. I have water. Okay. I'll take point A. I will take point B, measured from the same datum. Okay. And I'm going to call this ZB. I'm going to call this ZA or ZA and ZB. Okay. What will this be? Yeah, water depth, but what does that water depth signify? So that's our hydraulic grade line, right? So this is term. This one here is right. Conservation of energy tells us that plus some head loss. Okay. Ideal system, let's not worry about this. Okay. When do we worry more about head losses? If we have, let's say, a huge difference, which of these terms do you think makes a big difference to your head loss? HL is usually a function of what? Velocity head, right? FLV squared over 2GD or some K. Okay. Why? Because the head loss is a loss in turbulence, or like, it creates something that will, the kinetic energy is the best one to be lost. Okay. It's very hard to lose pressure and potential energy. We can convert all of them from one to another. That's what this statement says, but our losses are more. So what do you think of flows in groundwater? Fast, slow? Slow. Okay. Typically 1 feet per day, 1 meter per day type of order. Okay. If I take a small number, square it, what happens? It becomes even smaller, right? So if I take a low velocity and make it even smaller, my velocity head becomes very small. So it has that out, and we say it's approximately equal to 0. Okay. The second thing we do is, I still have 5 minutes, so I'm going to make use of it. This head loss will also be very small, and that will go away. Okay. So we just use these two to represent our heads in our model. Okay. So in groundwater, we seldom use the velocity head. We're only left with P over gamma plus Z terms. Okay. So this is what we call our heads, and the gradient would mean over that L, right? We can do this in surface water because we know the direction of our flow. If I say what is the direction of groundwater flow, how do you know? You can't see it. So what we need to do is we need to get 3 wells and then infer our head from it. Okay. So what we do is we fit a plane through those 3 heads. Okay. And we say H equals some value, and if I take del H over del X, that's my gradient in the X direction. That's my gradient in the Y direction. I can extend that to Z direction too if I want, but that's how we calculate the gradients. So let's stop here. Looks like there's another class that's going to come in, and then continue in the next class how advective transport and dispersive transport is done. But again, the take-home message is site characterization is extremely important because that helps us tell what the direction of the flow is. It helps us tell what the hydraulic conductivity is and all that good stuff that we need to know how are the pollutants.